Had a look at simple harmonic motion. This time I want to continue having a look at simple harmonic motion. I want to have a look at some of the formula, but before that I want to look at a real situation. And when we get real situations with simple harmonic motion, they're basically anything but simple, and generally they're damped systems. So what I want to do is I want to have a look at this to sort of see what you might be up against when we have a go at doing this. So what I've got set up is my Pasco software, and this is going to record what's going on. So if we just put that on so you can see the Pasco software, and as a previous couple of runs I've actually gone through, and let's see the equipment. So we'll just see if we can put the equipment up for us. There we've got a cart, and we've got a spring, and we can see this is going to move up and down. I'm just going to stop it. And what we're going to do is we're going to see if we can get ready to run this. So what I'm going to do is I'm going to start the recording of the software, and then I'm going to move the cart down, and let's see what happens. Now, what we can see going on here is that the oscillations aren't carrying on the same size as they did before, but they're going smaller and smaller and smaller as the cart is actually sort of using smaller and smaller movements. Now, the reason it's doing that is because I've got a massive spring, and it's more than the cart. We've had to put extra weights on the cart, and basically this now comes to a halt. It's also got a fair bit of friction as this spring is rubbing against the track. So there we are, it's now stopped. I'm having a busy few moments here. So, right, having got rid of the door, the phone and all the other bits and pieces, we can see that we've got here a nice gradual curve as this thing is gradually slowing down and stopping. So this is light dampening on our simple harmonic motion, that we're actually slowing this system down a little bit each time until it reaches a dead stop. So dampening is found in most sort of systems, and this is what we normally see when we play around with simple harmonic motion. When we try real life situations, then it's a little bit different than what we sometimes set up in the classroom. So that's damped harmonic motion. Now, let's see if we can get on and have a look at some other bits and pieces. Now, I had to do that one first because this setup is rather large and it sort of gets in the way of everything else, and we wanted to try and set this one up so that we can see it. So what I'm going to do is I'm going to take this now out the way so we can have a look at the rest of the experiments. And we'll just move this track out the way. There. Right, What else have we got here? Well, in this system I've got a simple pendulum. I've got it attached at the top here to a rotation sensor, and this rotation sensor, you can see, moves. Attached to the rotation sensor I've got a force sensor, and this force sensor then, when it moves, I have to move the wire out the way, there we are, that's better. What we'll get is we can measure now the angle that we've got, and we can also measure the force on this pendulum bob. It doesn't matter what force I actually use, how much mass I'm actually going to use on this pendulum bob. What matters really is the length of this string. So let's set up this experiment to have a look at. So if I call up the Pasco software, I'm just going to now basically get rid of this. So we'll have a new experiment, and I can discard those changes, and what we're going to do is I'm going to just make sure my hardware is set up, and I've got on here my different bits and pieces. I've got my force sensor and I've got my rotary motion sensor, and what we're going to do is going to have a look at a little graph of this, and probably not the best one to actually use. Let's see if I can just draw a graph. There. Right, I'm going to basically do two graphs. We're going to have a look at the force against time, and I'm going to look at here my angle, and I'm going to set this to degrees. So we're ready now to start this. So let's set the recording going, and what I'm going to do is I'm just going to swing the pendulum. And you can see we're getting some movement. Let's stop that. Now I'm going to change the force sensor here so we can now see this a little bit more clearly. And I can change the angle again so we can see this more clearly. Right, it's running, so let's record this again. Now what do we see with this? Well, I'm moving here across. Now the angle's not quite right because I did this halfway through a swing, but the angle's changing. But what we're actually seeing here is that we're getting a high force when we're one side, and we're getting a high force when we're the other side. Let's try that one again. I've steadied it. That's not going to be accurate enough, so let's start again. I've steadied it, and let's move this. So as it's now moving across, up and down, we can see what we've got going on with the forces and the angle. Let's just expand this one. They line up a little bit better now. I've got the angle here. So this is the center point. So as this swings down to a maximum, then we get a maximum force. And then when we move to the other side, we get another maximum force. So the force is greatest when the pendulum bob is at the extremes. And if we look at the pendulum, I'll show you exactly what I mean here. So our force is greatest when it's at this position. The force is least when it's in the center position, and then we get it also large force, the maximum, when it's at the other side of the swing. So we can see where our maximum force is going to be, as well as our maximum displacement, which we're measuring in degrees as we go along. This one, you notice, still dying out a little bit. We can set simple harmonic motion systems up, either be dedamped, or we can get them so that they are more continuous. So we've got this measurement here of a pendulum. Let's look at a little bit of the theory, and we'll see what other things we need to do to measure things when we look at the simple pendulum. Right. Now, the simple pendulum, what can we do? I'm going to go back onto the piece of paper in a sec. Right, there we go. We were trying to do some more fun with the picture-in-picture. The time period that we're looking at, t, equals something to do with motion in a circle, so it's going to be 2 pi, and then the root of L over G. L is the length of the pendulum, and that's going to be measured in meters, and it's measured to the center of the mass of the bob. So length, meters, but it is to the center of our little plumb bob. G is acceleration due to gravity, and that is going to be measured simply as 9.8 meters per second. And so we can work out what the period of this is going to be, as long as I know the length of my piece of string. Now, if we look at this pendulum, where am I going to actually measure from? So I'm going to measure from halfway in this mass. Now, it isn't actually going to be quite halfway because of the shape of it, but we're going to take it as halfway. And then I'm going to measure from that distance all the way up to the pivot point, which is in the middle of this device. So what I now need to do is measure that, and I'll get a ruler. Forgot one. I remembered everything else. I did quite well, I suppose. So I'm going to measure from halfway in this pendulum bob, and that gives me 83 centimetres. So it's about 83 centimetres. Okay, we've got 83 centimetres for our bob. Let's go back and have a look at what we've got here. So if I can work out our period, it's going to be 2 pi the root of 83 centimetres, so 0.83 metres, divided by 9.8 metres per second. Let's go and have a look at this and do the calculation. So this is going to be 2 times pi times the square root of 0.83 over 9.8. And that's going to give me about 1.82 seconds. Really 1.828, so let's call it 1.83 seconds. We're going to be lucky to see if we can actually measure that. So let's see this time if we can measure the time of our movement. So if I look at my graph here, then if we say that's 11 seconds going across to that one, then I've got 1.246. It's about 1.8 seconds just going and having a look at one of these movements. If I take that one there, 1.2468. So we've got a reasonable correlation here, and that's just looking here at something which is just the angle. I don't have to look at the angle, but we'll have a look at some of the others, and we're getting a reasonable correlation. Let's change this, because I didn't just record the angle here. What I also recorded was my position. And if I record my position, then looking at this bottom graph here, we can measure the distance here, which is 0.4, so that's 1.4, 1.6, 1.8. So we've got a measurement here of our t, our period, and it seems to work quite nicely with what we've got. So what else can we do with this formula? Well, once you've got this formula, we can start getting clever, and we could in fact do things the other way, and we could start measuring things like gravity. Now, I will point out at this moment in time that where I'm sitting is a geographical anomaly for gravity. I know that because every student that comes here seems to get wide-ranging different values for gravity when they work it out. It does worry me that sometimes we beat Jupiter for its gravity, and other places we actually achieve something called negative gravity. I have no idea what that is, but that's just mistakes in calculations. So, can we work out gravity from this? Yeah, because all I need to know is the time period, and we can work out what gravity is going to be. And we can work that out because if we look at T here equals, and what we could do is we could rearrange this formula and make it 2 pi divided by the root of g times the root of L, the length. And if I want to think about that, that gives me a y equals mx plus c type graph. Well, hang on, that's going to be x, isn't it? There's going to be my constant. There's going to be my x plus c, my constant. And so if I could draw a graph of the different periods against the square root of the lengths, then what we should get is a graph. And the gradient of that graph will be 2 pi over the square root of g. So we should be able to work out here a value of g. So all I would need to do for this is to vary the length of the string, work out the period each time, and we could work out a value for gravity. And it seems to be quite accurate what we can do with this. So that is looking at this formula, which is here the period relating the length of the pendulum to here gravity. Notice there's nothing about the mass, so we can increase, decrease the mass, and it makes no difference. So that's one of our formulas we can have a look at. Let's have a look at some more. The first of these we need to know is that basically if I take some sort of setup, and if we have some sort of perhaps spring here with a mass on it, and we did that experiment last time, but we're probably going to need that one again this time. So let's see what we can set up. I'm just going to need to set up a little experiment here. So I'm going to take my force sensor off. I'm not going to need my string, and what I'm going to do with this is I'm just going to modify it, put a different type of connector in it, and this I'm then going to put into the ceiling. Let's hang that out the way. Badly, in fact. It'll do. I can then hook over my spring, and then we can put a weight on this. But what I'm going to do is take a different type of sensor here, and this is my ultrasonic sensor, and then let's put a small mass on here. Now this period will depend on the mass because we're doing a different experiment. And we'll line this up, line it up over my sensor, and then let's set up this software. So what I've got is a different hardware setup, so I'm going to have a new experiment. I'll discard that. My new hardware I've got a high resolution 4 sensor, and we've got a motion sensor. I'm not using my smart cart. I will just turn that off. So let's have a look at what's happening in this graph. So now let's not bother with, I can bother with data, yeah, let's do that. Now what measurements are we going to want this time? Well, I'm going to take the force, but we're also going to want to measure here our position. Bearing in mind this time this is a spring. And the beauty of this Pasco software, of course, is that we can swap this information at any time. So let's set this spring going. So I'm going to see if I can get the spring going. We're trying some more clever picture-in-picture today to try and help you see what's going on. It looks like it's in about the right place. Let's have a look. And we can get the force, and we can get the position, and I've got my data if I need it. And that's probably easier for you to see. I don't need such big spaces on my data. And I am going to just stop the pendulum moving because I'm rather frightened I'm going to clunk my head on it. Okay, so let's look at now another relationship that we want to do, and that's going to be looking at things like acceleration and displacement. Now, what have we got? Well, I've measured force, that doesn't matter here, but I want to look at acceleration, and acceleration here is going to equal minus 2 pi f all squared times the displacement. A here is our acceleration. 2 pi is fairly easy to work out. F is going to be our frequency, and we know that our frequency is equal to 1 over t, 1 over our period, and then we've also got x here, which is our displacement. So we've got our displacement from the centre. So we've got our spring set up, ready to go. We know it works, and I'm just going to settle my spring down so it's at the right place. So we're going to do a new experiment now, the same experiment. I can measure on here not just the position, but I can measure here the acceleration. So I've got here our point where it is going to be, no problem. Everything's ready to go, and so let's set this one running. So I'm now going to record. Let's just pull this down, set it going. It takes a couple of goes to try and sort of settle down. And there should do it. So let's take this off, only because I don't want to clunk my head, and let's have a look at some of this data to see what we've got. Now we can actually here measure the acceleration, or I can just measure the displacement. Now our neutral position here was 0.32 meters away from the base, and it went down as far as 0.21 something. Don't worry, I can measure that in a minute. And we went up to there, which is about 0.43. So we can measure what these are. So I can measure my displacement, and when we're trying to look at our displacement, we have to think about what we're talking about. If I draw one of these graphs, not very well drawn. The distance from the center point to the highest is our amplitude. Our displacement is the distance from the very bottom to the very top, and so we've got to decide here what we want to try and work out. Now, what else do I know? Well, I also know that the expression 2 pi f also happens to be the angular frequency. Often given the symbol there of little omega. Why is there a minus sign in this equation? Well, this is because the acceleration is always back towards the center. So the acceleration is always in the opposite direction to the displacement. Our maximum displacement is called the amplitude, and of course that A does confuse people with that A for acceleration. So let's see what we can gain from our results. So looking at our results, I've got my position, and we can look at this data and we can see where I started. So if we look at our minimum, it was here at 0.21 meters. So I can write that one down, and our maximum here is going to be 0.43 meters. So we can very simply just work out that calculation. I know it's a very easy one to do. 0.43 minus 0.21 gives us here 0.22. So there's X worked out. Now my problem is we've got to work out the frequency. I don't know the frequency, but what we can do is we can work out the period here. Now I didn't bother to try and record that. I could have easily have put in a time, and it just so happens that I could have put in the time. So if we measure, that was 6 seconds to here 6.6. The time period to go halfway is going to be from 6 seconds to 6.6, and to return again to that minimum value, we've got here about 7.3. So that's going to give me my time period of 1.3 seconds. So now I've got my 1.3 seconds, we can simply work out my frequency, and my frequency is going to be 1 over my 1.3 seconds. And yeah, this calculator could have done it with one button, but we can work out my frequency here is going to be 0.769. So let's see if we can work out my acceleration. My acceleration is going to equal minus, then it's going to be 2 times pi times the frequency, 0.77 for the accuracy we've got squared, times my displacement, which is 0.22 meters. Let's work the calculation out. So I've got that number times pi, I made a mistake, times 2. That's all going to be squared, and then let's multiply that by my displacement 0.22, and that's going to give me an acceleration here of 5.139 meters per second minus, because it's going to be towards the center of the movement. Can I check that? He worries and panics up for a moment, but if we've got our acceleration in meters per second, then according to this we've got about here minus about 2.25. We can check what the acceleration is. And we can see that it's going up here. Minus 2.35. So I've got here on this system exactly really half. But that is right, because that is our displacement. If I measure when it was only a certain distance away, we should be able to work out what our acceleration is, because remember that is our displacement. So if I worked out when it was only halfway away, its maximum, it's going to be that number, so it's going to be half of that, and that exactly corresponds to our data. So it all seems to work quite nicely. Okay, so we've looked at acceleration, displacement. What other things can we do? Can we link in anything else? So let's see if we can look at velocity and displacement. If we look at velocity and displacement, we know that our velocity here is going to equal plus or minus 2 pi f times the square root of the amplitude squared minus the displacement squared. So we've got, for our example we've already done, we've got some figures that we can use to try and help us work some of these bits and pieces out. So we have my 2 pi f, that equals 2 times pi times 0.77, and then we're going to multiply that by the square root of the amplitude, and we know our amplitude because our amplitude was equal to 0.11, and we've got our displacement, and what can we know about our displacement? Well, that's the distance here, and at maximum displacement we know that that actually equals the amplitude, and we know that that must be 0. So we can rearrange this to say that our maximum velocity is going to equal, plus or minus, because it's going to go in either direction, 2 pi f times our amplitude. So we've got here 2 times pi times 0.77 times our amplitude 0.11, and that should give us our maximum velocity. Now, it just so happens that I actually recorded our maximum velocity, and I can put that in there. So we can work out here my maximum velocity. I've got 0.51 minus 0.51, so that's our maximum velocity. So plus or minus 0.51, that's what we actually had. Let's see what we get theoretically. So let's cancel that, and we're going to put in 2 times pi times my 0.77, and we're going to multiply that by my amplitude 0.11. I keep my fingers crossed, and it comes out at here 0.53. Now, if this is the first value, it might have got lower, so let's just check. And no, it was, we managed 0.51. So I'm quite reasonably happy with that. Judging by how some of my experiments go, that's a pretty good result. So we've got our acceleration, we've got our velocity here, spot on. So we've got our actual, and we've got our theoretical number there. We started having a look at one with energy and simple harmonic motion. I want to draw a little graph of here. I've got my amplitude, my minimum amplitude, I'll have my maximum amplitude, and here it's going to be set to 0. And if we look at this as my energy on this side, then what we've got is a graph of my KE. At the extremes, my KE is going to be 0. So this is my plot for kinetic energy. If I look at my plot for my total potential energy, then it's going to be a maximum at the maximum amplitudes and a minimum the other side. Minimum in the middle, maximum the other side. So this is what we've got, and if we add those two together, then we should find that my total energy is in fact going to stay the same. So we've looked at a few bits and pieces here of simple harmonic motion. We've got this idea of energy against displacement, and we've managed to work out a few of these different problems. So hopefully that gives you some idea of some of these functions, the idea behind the ticking clock with its pendulum or with its spring going. Either sort of don't make an awful lot of difference. They both keep remarkably good time. And we've looked at our graphs previously, but also we've looked at some of these today where we can look at the difference between, if I can get it right, my position and that's our position, and you can see that the force corresponds exactly with our position. If I compare that then with my velocity is 90 degrees out of phase because it will be fastest at the midpoint, midpoint. And then if we look at my acceleration, this is opposite to the graph of the position. Look at this point here, and we'll see that if I go to position, it's 180 degrees out of phase with the position, the acceleration. So we've got our three graphs that sort of explain what's going on. Now, the only one that's really missing from this is the experiment where I take the pendulum, I swing the pendulum with something like a paintbrush at the bottom, and I pull a piece of paper, and I can show that you get this sinusoidal wave out. My experience with using a paint pot, a paintbrush, paper and some science equipment usually works out fairly badly, and my experiences with using this, it doesn't work terribly well. It works better if you can put sand or paint in a pot or something like a syringe and do that, and you can move it and see what happens. My experiences are they're not very good. So there we are, we've covered most of the formula of simple harmonic motion. Remember about dampening though, this idea that in real life normal simple harmonic motion is often damped and got rid of. So thank you for watching this A-level physics topic by topic. If you liked it, please subscribe, and I'll see you again next time. Take care. Bye bye.